Welcome back to the Hyperbolic Coding Chamber. This is day 64 of Daily LeetCode. Daily LeetCode. We are back once again. Yesterday, we dropped an absolute banger, the first movie in a set of a new trilogy called The Tortoise and the Hare. Today's video is probably going to be called The Hare and the Tortoise. Or no, maybe it's going to be called Tortoise and the Hare 2 Electric Boogaloo, I think is what this one is going to be called. But reflections, we had a good legendary comment from Thomas Wong, the legendary LeetCode master himself. This man is doing approximately 3 hours of LeetCode a day. This is crazy, right? So this man, I mean, we already know, right? Thomas is low-key our guiding light. Thomas is low-key our guiding light in the sea of despair and darkness that is figuring out how to solve LeetCode problems. And then there's also another comment from Oh Dang. And he mentioned, is it a good idea to start LeetCode while starting to learn code, or should I start after learning the basics? I think this is a tough question to answer. I'm still pretty new myself. I've only been programming I wouldn't even say professionally, because I'm really an imposter. Maybe like a year and a half. And then before that, I had like a bunch of smaller personal projects, kind of around like when I started college. But yeah, should you LeetCode while starting the basics? I personally think it's easier to learn. I always think it's easier to learn when like the locus of control is centered around like application. So I don't know, like I remember in school, like you'd have a math problem to do, right? And the teacher would explain it to you in class and it'd just be really hard to understand. Then afterwards, you'd go home and you'd do like 40 math problems and you'd be like, oh, okay, like now I get what they were saying. So I feel like learning a lot is like that. So sometimes like learning through Code Academy, or a lot of these other platforms, you're kind of learning by doing, which is pretty dope. But also I think there gets to a point where, you know, you're always learning on a rail, right? On rails. When you go off the rails, you kind of might feel like, you know, what should I do? So I think learning to code while LeetCoding, that would be like hard mode or like extremely hard mode. But I think there's a lot of rewards there for, you know, if you're willing to stick through it. But I think it's easier to just learn from a platform that you like and then, you know, supplement it with a project that you enjoy, like something cool. I think I started programming when I tried to make this silly, you know, clone of like Flappy Bird or something, and that kind of, you know, kept me interested, kept me excited. So maybe that could be useful, but yeah, I think we definitely need more. I guess I would say that's the best answer I can come up with, but you're going to want to know the answer to this question, right? Because Elon Musk is in the Discord, so you're going to want to get that answer from him. But the only way to get the answer is to join the Hyperbolic Coding Chamber, which is the Discord of this channel. Reflections on yesterday's coding, though. Yesterday we were working on a problem called number of provinces, right? For which we do know a solution for, right? We're basically being asked to count the number of connected components, but typically we do that with the union find data structure, a disjoint set, right? But we tried to do a different version of this, which basically you can create, right? Due to the nature of the breadth first search, you can create, you know, a parent array, which is very similar to the root array in union find, right? To be able to figure out the number of connected components. So I think today we're going to try and finish up this problem. And I think it got a little convoluted since we're doing a BFS over an adjacency matrix, but I think it's still a good exercise to figure out how to make sense of something like that. And I think near the end of this one, right, we had a lot of trouble calculating the output just because, right, you have a problem, you're trying to solve it, right? You're coming in fresh, you know, 10 minutes in, 20 minutes in, it's kind of like a timer, right? Or intensity, you're calculating the numbers, you're pulling them around, you're moving things around in your head. Near the end, right, you just kind of, I just started guessing at the end. So instead of making sure that the problem I'm solving actually makes sense, I literally just started like deleting lines or changing this vertex to this V and this one to that one. So there's a few different problems with the method I went about doing this. I chose some poor variable names. And so overall, I ended up it got kind of confusing to reason about the code. So it just be like that. And even in the end, the time complexity of this solution is like n squared, I think. So it's not really much better than union find anyway. But I think I just wanted to make sure to do it this way, just as like a way to grow, because I already understand why this works with union find, but I want to make sure I can create something similar with BFS, and it could be a useful tool to have in one's arsenal. So that's what happened yesterday. We're basically trolling, going too quickly, right? Not really making much sense of it. Also, another reflection that I'm realizing is does it make sense to work on graph problems when we don't have the basics covered? So I got stuck on a string problem earlier today with sliding window, and I'm just realizing that I think there was a better way I could have went about it, and I'm realizing ultimately I solved the problem, but I think it's just a strange thing, right? It's kind of like if you get really good at something, like imagine you're an artist, like maybe you can write, maybe you can draw like a cathedral in Rome or something, right, with perfect detail and accuracy, but you can't draw a person. That's kind of what it feels like. So I'm thinking after this graph explore card, we're probably just going to go to strings and just work our way up, or maybe just go through data structure cards. But yeah, I think, yeah, that was just strange. I guess I feel like I should have more of that, like more of that. I guess I should have a better, like in terms of skill, in terms of these like simpler problems like strings and stuff like that. But yeah, that was just something I was thinking about. But yes. Other reflections on yesterday, there was another problem we did, I think, relating to binary trees. That was pretty cool. So we're slowly making it through there. And I just flipped around today's schedule a little bit. Usually I do, and this kind of gets back to Thomas's comment earlier. Usually I do like an hour to an hour and a half of LeetCode, and then I'll try to read or watch a lecture on system design. That's like 30 minutes. Then some more supplemental reading with the algorithm design man. So it's like maybe 2.5 hours every day. The legendary man himself, T. Wong, right, is doing 3. I don't know if we can get to 3. There was a time about 2 weeks ago we were doing about 6 hours a day, and it just wasn't working out. It was working in a sense, but it was also unsustainable in another sense. So that's why yesterday's video was called Tortoise in the Hare. This one's going to be called Tortoise in the Hare 2 Electric Boogaloo. And this is going to be part of a three-layered, a 3-tiered movie. So this is part 2, and this one's a nail biter, right? So we're going to be working on a number of provinces today. And now, actually, I think for the first time today in the channel, I always start the video by saying we're going to do X and then we do Y. Yesterday we said we're going to do X and we did X. So today we said yesterday we said we're going to do X. So today we're also going to do X. That means is we're going to be revisiting old problems, right? And trying them in new ways if we have a new solution in mind, right? And I was actually kind of hoping I'd get to read before I tried a number of provinces with this BFS algorithm. Unfortunately, that is not the case. So we're kind of missing a chance to read there or to integrate, right? A piece of knowledge from the supplemental reading into the problem solving. That is ultimately very unfortunate, but it is what it is. So we'll go on with number of provinces, right? And just reality is we're just gonna have to put evaluate division on the back burner. This problem is unsolvable, actually unsolvable. If anyone solves this problem, let me know, because I'm fairly certain that this is a farce. The 300K solved here is a lie. But that being said, we're going to do number of provinces and then see what else we have to do after we refresh this page. But I don't want to lose my pass fail button. So that being said, yeah. So we're going to be doing LeetCode. So let me know if you're doing something similar. Let me know, how many hours of LeetCode are you doing? How are you doing it? Right? Are you following a guide? Are you doing the grind 75, the LeetCode 150? Are you doing it daily? Do you do 2 times a week, 3 times a week? I'd be interested just for some data collection purposes. But yeah, so we have an hour on the clock, so we can just jump into it, right? So I'll start this. So let us begin. Also, don't forget to join the Hyperbolic Coding Chamber. This is the hottest Discord, right? We have hundreds of millions of people in the Discord currently, so you're going to want to join before it's too late. So I think I remember what we were going for. This problem is ultimately asking us to count the number of connected components, right? We know that this is solvable with union find, data structure, right? But I know that from the ADM, there was a breadth first search method, right, that you could use to generate a parent array. And this generally creates an array of elements, right? Where we'll have 0, 1, 2, 3, 4, and 5 per se, right? If we have, let's for example, say we have example 1 here, we have up to 3 vertices, 0 indexed, and for each element in the array, right, we'll store the parent of that element. So they're all actually going to start at -1, right? And the ideal outcome, right, for this set of connected edges would be a parent array, right? If we copy this, would look something like this, right? The parent of node 0, right, which is really node 1, right, is going to be -1, right, because it has no parent. The parent of 2, however, is going to be node 0. Oops, sorry, it should be node 0, right? And then the parent of 2 should stay -1, right? That actually does make sense. So I'm curious to see, right, if we're getting the current correct output, right, for our parent matrix, and do we print it? We do print it, right? And let's check what our current test case is. Let's change our current test case to example 1 just to make sure that it makes sense. So, right, so we know that we're not producing the correct, we know for certain that we're not producing the correct output, right? Because there is no connection whatsoever to either of these 2 vertices to connection 3, yet our node right here is saying 1. So the method by which we're creating this parent array is incorrect. So what is our current method? So it looks like we're trying to do a BFS over the adjacency matrix, right? We have a number of provinces, which we can probably move below, since this is something we'll be concerned with later on. Right, we have a set, and I'll make this slightly smaller again. We have a set, right? And let's just change this to scene, right? This is just gonna help us reason about the code a bit better. Right, so you have the scene set, right? It looks like we're going to iterate over every vertice available, right? So we're gonna start with vertex 0, we're gonna put it into a queue, and while the queue isn't empty, we're gonna do a BFS starting from this vertex, right? Have we seen vertex 1 before? We haven't, right? So we're going to add it, and then we're gonna print the vertice. Right, so what's the distinction here, right? Vertice, right, is actually the current vertice that we're at, right? So it's distinctly different. It is distinctly different than V, which is where our BFS started at. Right? So I think it actually makes more sense. What if we renamed vertice, right, to cur, right? So now this is more readable, right? We pull the current vertice off the queue. We haven't seen it before, so we add it, right? So now we've seen one. Now you want to we want to push all of one's neighbors, right, onto our queue to be processed. So the way we do that, right? We want to iterate over NIDX. Now, what does NIDX mean? Our goal really is just to, for this V, right, which is actually 0, we'd like to go to this row, the 0th row, and is connected and iterate over the elements, right? So we're saying NIDX is equal to 0, NIDX is less than, is connected, subcur, so NIDX must be the neighbor's index. So maybe we'll change NIDX is the neighbor's index. So let's just keep going with that. For now, all right, is less than is connected subcur.length, all right? And then to get the the actual, to test, so neighbor V is actually not neighbor V. Neighbor V, with this value here of subcur sub NIDX, would test if there's a connection, right, between cur and NIDX. Right, so neighbor V is already off. So if NIDX is not equal V, right, because we'd like to skip, we don't want to include ourselves in the BFS, right, because V is 0, right? So now we're iterating over this array. We're going to say if 0, right, vertex 0 does not equal V, right, but 0 does equal 0, right, but let's pretend, right, that we're in yeah, so 0 would not equal 0, so we'd skip it. So then up here, right, remember, because this is an adjacency matrix, right, what this really says, right, is it's really talking about a connection between these 2 points, between these 2 nodes. So when V is equal to V, right, so when NIDX, which is where we started at, this row sub 0, right, is the same, because we're iterating over the row of neighbors, right? So if our index, right, if NIDX is equal to, does not equal V, then we're in business, right? Because 0 would equal 0. We'd want to skip that. That would be ourselves. So now let's say we go to the next index when NIDX is equal to 1, right? And NIDX is not equal V. So that I think that does make sense. Yeah, so I'm seeing, yeah, this was all over the place, right? So the first thing we want to do is make sure that there's a connection there. Because if there's a connection there, right, and NIDX is not equal V, and we haven't seen this index before, then we'd like to do, the BFS, right? And if that's the case, our parent would not, if we are at a current index, right, what we really want to say is that the current node that we're at, parent, is actually going to be V, because V is where the BFS started. So no matter how deep we go, our parent is going to be V, right? But then what we'd want to push on is actually is connected. We actually want to push on is NIDX. So let's see if this makes sense, right? So we're gonna start with, right? If we just start with our example here, we're going to have 1 in the queue, right? The queue isn't empty. We're gonna pull off 1. Have we seen 1 before? We haven't, so we add it. And we're gonna iterate over the neighbors of cur, which is actually, I said 1, but it's 0 indexed, for the vertices. So we're going to look at the 0th row, which is the first row, and iterate over those values. Now, are we connected at 0 sub 0? We are, but NIDX is 0 and V is also 0, so we're going to skip this. Now we're going to be at our second value, right, which is this 1 here, right? And V is still going to be 0 because that's where we started, right? So we're going to pull off. Oh, no, right. So now NIDX is going to be equal to 1, right? Is connected right. And so is connected sub 0 sub NIDX, right? Does that equal 1? It does. NIDX actually equal to 1 and V is equal to 0. They're not the same, and we haven't seen 1 before. So we're going to say for this current index, which is index 1, its parent is going to be V, which is 0. Then we're going to push NIDX. Right? We go to NIDX equals 2, right? But there's no connection there because it equals 0, right? And we're saying 2, but it's 0 index. So when we say 2, we mean 1, which would be this node right here, right? Or this row right here. All right, so now we're going to go back to the top of the queue. We're going to go back to the top, right? The queue is not empty because 1 is in it. And we're going to say, okay, have we seen 1 before? We're going to pull 1 off the queue. Have we seen 1 before? We haven't, so we're going to add it. Then we want to visit all of 1's neighbors, right? There's a connection with itself, but NIDX does equal V, so we're going to skip it. Oh, no, equals 0, right? NIDX equals 0. There's a connection, and 0 does not equal V, but we have seen 0 before, so we'll skip it. Then we're going to skip 1 because it's the same. Then we're going to go to 0. The thing, though, if there was a connection in this third quadrant here, if this was a 1, right, we would say parent sub cur, right? We would say parent of we'd say parent of cur is equal to, what we really want to say is the parent of NIDX is equal to V, and then we push NIDX on. Okay, so now this works for our first test case. Let's test for a test case with 3 provinces. Okay, so let's see if we can get through. Oh man, that's crazy. That is actually crazy. Yeah, it's interesting. You can come back to it. This one's going to be called Tortoise in the Hare 2 Electric Boogaloo. It's just interesting to see when you come back to the problem. It's just very interesting to see when you come back to the problem that you can see it so much clearer. Now we know that this is possible, right? And the time complexity here should be, in the end, we're only visiting each node once, right? We know we have a for loop and a while loop, but V, right, we make sure, right, that for each V, right, we want to visit all of its neighbors, right, just to ensure that, right? And if we're going to ensure that, right, if we've seen a node, right, we add all of its neighbors, which means we only end up processing all the nodes once. But since we're using an adjacency matrix, I guess our time complexity would be n by n. N by n. N by n. Down here, we assume that, right, the worst case, right, that they're not all connected at all. And then we iterate over each of them, and if it doesn't equal -1, which means it doesn't have a parent, then we subtract 1 from provinces. So I would say this would be n by n, or n. Yeah, so that's kind of what we said, it's n squared. So it's basically saying that was really cool. That was pretty cool. That was really cool. Feel strong, man. So they do this with the DFS too. The time complexity is also. Wait, this is literally what we did here. They're iterating over the map, iterating over the matrix, right? Visits by equals 0. Ah, that's interesting. We could have done something similar. We can remove the map and just use visited as well. We're using a pretty much an integer array for visited instead of a set. While q isn't empty, right there, move it, visited sub s equals 1. And if there's a connection, and if we haven't visited, then we add it. I guess we don't have to check that nidx not equal v, because if we're visiting v, right, then we can guarantee that, for example, if we're visiting y, right, we can guarantee that y is a parent of x. If that's the case, right, even if we add x onto the queue, we'll never visit it again because we make sure that we don't. I think the reason, I think if we resubmit this, we should still get it true for all of them. So yeah, that was unnecessary. You could compress connected into this. And I guess another way we could do this that you don't have to iterate over provinces -1, if we let provinces equal is connected dot length, right? Whenever we make a connection here, we're going to want to do provinces minus equal 1. Oh, so that actually is not. Right, that actually not quite the same. I think what we'd probably want is, you know what? Maybe we'll keep what we had. Oh, I still have provinces and minus equal 1 here. So that's interesting. I think that's fine. I think, to be honest, this one seems faster. This one seems faster than union find, because union finds an average around 130. So I wonder why that is. I think it's because, actually not. Yeah, I think it's because someone actually says in the discussion that the union find approach would actually be n squared in his opinion. So that's interesting. I'm interested later to read the ADM on actually. I don't get why they're adding count here. Visited equals 0, right? Which means we haven't visited it. Then we want to visit this vertex. All Q is empty. All the Q is empty. Then we're going to do the DFS. All right, we'll set S equal to 1, so that we visit it. It's equal to 0. If there's a connection and if we haven't visited this neighbor, then we'll add it. After the BFS, we'll do count plus plus. Oh, I see what they're saying. Right, this only runs if we haven't visited it. Right, so if we're presumably, right, if the nodes are connected, we'll visit them all with the BFS. If we find another node that's not connected, then we would just do count plus plus. So I think what we were going for earlier could actually be kept. We just need to reverse it. But I think it would actually be down here, right? If we add a node, right, because we've seen it. No, that's not exactly where. We'd want something outside of here, like right, since we're going to be iterating through all the vertices, right? We want something encapsulating, like if we have not seen, right, if we do not have V, then we'll do provinces minus equal 1. It's actually quite tough, right? Because it's before we actually start processing them. I think we could actually do it. We kept our original line. I think the problem no, it doesn't make sense. If we're visiting it, then if we've seen a node before, if we haven't seen a node before, right? So when we say if we haven't seen, it's not exactly the angle that we're looking for. I'm thinking it's actually the opposite. If we have seen a node before, then we'd like to subtract from provinces. Okay, yeah, okay. So this makes sense. So I would say, yeah. So we found we had to compress a lot of the code that was just there for no reason. It looks like it's hard to do better than n squared and n time. So I would say that's a cool solution. And another way that we've kind of tied like a dendritic swamp tentacle or vine to union find. So that's pretty cool. Yeah, that's an awesome way to close this problem out. So we have symmetric tree. Given the root of a binary tree, check whether it is a mirror of itself, symmetric around its center. Symmetric against itself. So if we're checking if a binary tree is symmetric against itself, right, then we want a symmetric around its center. So basically, I mean, if we fold this in half, if we folded this in half, would they line up together? So I think in this case, it's true. And I think we can see that, right? Because if we fold 2 to 2, it matches up. 4 to 4 matches up. And 3 to 3 matches up. Right? But it's interesting, right? Because we're not exactly checking, right, that 2 matches 2, right? If you have a node with 2, it's left, so left subtree is 3, right? But in this one, this 2 is left subtree is 4, and they have to be different in that way because we're folding them on top of each other, right? So they actually have to be a mirror and not exactly the same. I think that's what we see with this one. If we fold this one across its center, right, they actually don't overlap. So I think there's a couple different ways you could solve this, right? There's one, right, where I think you work with this recursively. You could start at a particular root node, right? And it looks like our root node always exists, right? Maybe when a node has no children, right? Maybe it's considered symmetric across itself. So if we can do this recursively, maybe we can start at 1, go to the left subtree, right, with the right subtree. Maybe we'll call a function called isSymmetric, and the goal will be to pretty much cross compare the nodes. So we give 2, if we pass this node and this node into this function, we'd want them to compare, right, its node's left subtree, right, with this node's right subtree, this node's right subtree with this node's left subtree. If we do it this way, I think we should be able to follow them down. So if we pass in left and right into this function, right, on the next recursive call on the call stack, I will have a pointer, right, to left and right on top of the screen, right? So let's say we want to go a little bit further, right? Then we could check left with left and right with right, and then right with right and right with left, right? And then this would go even further again. So we can try that right here, and we'll just return symmetric, right? And what we can do is pass in root.left and root.right. What we do is maybe have this function, we'll just call it sim. Take, you know, node 1, which will be a tree node, or null, and node 2, which could be a tree node, or null, and we're going to return a Boolean value. So there's a special way I think we have to go about this, right? Because if both nodes don't exist, right? If both nodes don't exist, that seems to be good, right? They're still symmetrical. We know that this is true because both 3 and 4 for both of these subtrees have those no values, and we're still returning true. All right, so the first thing we want to do is say if node 1 equals null and node 2 equals null, right? We want to return true, right? So also this works with when our root tree node has no children, it'll return true. Then additionally, right, if node 1 does not equal null or node 2 does not equal null, right, then we're going to want to return false. And the reason that is because if we know that both of these are not null, right, then we know, right, that at least either both of them have values, right, or one of them doesn't have value. So in the second case, we check, hey, does one of you not have value? And we can check that pretty safely, right, because we checked up here, because if they both have no value, we'll return true, right? So that leaves the only case where this line 18 would run, right, is where node 1 equals, some value, right? Node 2 equals some value, or we have node 1 is null, right, and 2 equals some sort of value. And we'll see, right, if node 1 value does not equal null, right, or node 2 value does not equal null, return false, right? In the case where both have a value, right, we actually make it past this point, right? So the only thing we actually do, right, we catch is this one. If one of them, if they're not matching in terms of pairs here, right, then we're going to return false. So from here, we'll likely want to have this propagate upwards. So we have this sim function, right? We're trying to solve for the first case, right? And hope that this translates to the entire tree, right? So we have 2 subtree nodes here, right? So we're going to want to pretty much, right? So if both values exist, then what do we want to do? We first want to make sure, right, that they're both the same value. So we'll say node 1 dot val equals node 2 dot val. And if that's the case, then we'll go even further, right, and make sure that the trees match, that those subtrees also follow the same rule. To do that, we call sim, right, with node 1 dot left, right, 3, right, and node 2 dot right, which is this 3, right, and then we call it with sim of node 1 dot right with node 2 dot left. And this does make sense, so let's give it a shot. So we're failing, right? So let's check. Oh, I'm thinking that case here is wrong. It's if node 1 equals null, right? Or node 2 equals null. And I think that was a typo in my head. So this would run in, right, we have image pairwise check right here, and we check against the node values, right, 2, 3, 2, 3, 2, 4, 2, 4. I think we would do n over 2 operations or linear time with linear space. Right, and tree once, linear space as well. So I think I'm curious to see if this could be solved in terms of just array values, and I feel like it could, right? Because if we know they're given a tree, right, I mean, it's actually not the worst thing in the world, since when the node values don't exist, right, we make sure that they both match, right? So the follow-up is, could you solve both recursively and iteratively, right? Can we just check these pairwise values, right? Because if each node has 2 values, right, after the first node, right? So the subtree for 2 is 3, 4, right? If we want to make sure that 2 dot left exists, we'll just take that current index, which is index 1, and add 2 to it, right, which would give us 3. Right, if we have another index, which is this one, we want to check that it matches its right. To do that, we would just add 3 to it. 1, 2, we add 4 to it. We need a longer array to really test this. We need a longer array if we have 1, 2, 2, and 3, 4, 4, and 3. Imagine we had a value over here. We have 3, 4, and 4, 3, which means that this node's children would come here, right? To get this 3, the first 3, right? Left child, you have to do 1, 2, 3, 4. So I'm wondering if that offset value is just 1 plus the level. Right? So when you get 1, 2, 2, right, your level is actually going to be 2. Do 3 plus the level, right? Start at so let's just say here, right, at 1, our level is 1, right? To get the value that's to the left of this 2, we do this index, which is 1, plus the level plus 1, which would be here, right? And then this one we do plus 1 plus the level. The level is 1 plus 2, right? So maybe 3, let's pretend that 3 had a child, right? This child would be here, right? The level would now be 3, so we do 1 plus 3, so 1, 2, 3, 4. So I think we could try a iteration based one. Maybe we could keep track of level. Right, and we're going to do some subset of operations, right? And if it's ever false, we'll return false. Assuming we make it through, we'll return true. Let's say level starts. We can always, I guess we can presume that level starts at 1 because there's always at least one node. So if level starts at 1, right, then the index we're going to start at is index 0. Right? So what we can actually do is just do I equals 0. I is less than, oh, we actually, just realized we don't actually get this value as an array, we get it as a tree. So how can we get this root to a tree, this tree to an array? So this is the output. We have 1, 2, 2, 3, 4, 4, 3. If that is the case, let's say we do an in-order traversal, right? I definitely don't think that's what we're looking for because 3 isn't the first value. So let's try pre-order, right? With pre-order, we'll print 1 first, then go left, right? Then print 2, then go left. Can't go left, so we print 3. Maybe it's post order. I think this array is just one way of representing it. I don't know if it's actually possible to get. 3, 4. I think we could get the array that we're looking for with the, I'm realizing now with just a level order traversal, 1, 2, 2, 3, 4, 4, 3. So to do that, we could just say R is equal to an empty array, right? And for this queue, right, we're going to start the queue with the root, right? And we'll say while queue.length is not equal 0, right? And then we're going to say const cur is equal to queue.shift to take the first node off the queue. Once we do that, we'll make sure, actually, we're okay if it doesn't exist. What we'd like to do is do cur.push root, right? Root.val or null, and I'm saying cur. What I'm looking for is r.push cur.value with nullish coalescing to null, right? And then we're going to do push q.push cur.left, right? And then cur.right. So I think we should get what we're looking for. Oh, I guess in this way it never ends, right? So we need a way of naturally stopping. I think it's fine, actually. We don't actually have to push. I don't think we have to push the value onto the queue if it doesn't exist, but we do have to push the value. I think we do have to push the value onto the array though. And then here we can say if cur, right, then we want to push, if, right, cur.left exists, right, then we want to push cur.right. And we want to actually push the value Okay, I guess I'm seeing now we only want to pre-push them onto the array. So I'm realizing when we do a level order traversal and we actually want to have the null values process, we had an issue. So we're pulling a value off the front of the queue. Problem being, right, that we usually ignore null values. So if we say that cur does exist, right, then we want to work with it. We want to push its children on to continue the process. But let's just say we push its child on and it doesn't exist. If it doesn't exist, then that's okay. I think there's a way we can do this. We just need two different delimiters. If we say cur.left, right, equals null, right, then we'd like to not necessarily push them onto the array, right? But let's just say cur.left equals null. What we're actually going to push on is actually null. I think what I'm trying to say is, or we don't want to process, right? If cur does not equal undefined, right, then we'd like to do work. So that's an easier way to put it, right? When we have cur, right, and let's just say the value doesn't exist and we'll push null on, that's fine, right? But if cur.left equals null, and we push on to the queue is going to be null. When we get to, there's another iterative version of this that you can do with the regular BFS. I guess I really wanted this version of it to work, right, where we try to do something with the array itself. So if cur, so we have one, all right, let's say we have no children, right, we pull cur off, right, and then we'd say, okay, does cur not equal undefined? It doesn't, right? So we push one onto it, right? Now we'll be getting null, null, that's what we want. Does cur.left equal null? So we now know the default values are undefined. So if that's the case, right, then if cur.left equals undefined, well, that's actually getting convoluted, right? Because if our value is null, we have to change pretty much the What if we wrote our regular BFS and see if we could make it make sense? All right, we have cur.val. All right, and if cur.right, then we want to push it. Same thing. We'll change this to right actually. This one to left. So I think we should get an output array here, but it's going to be lacking the null values. We have 1, 2, 2, 3, 4, 4, 4, 3. Problem is when we actually have, it's kind of hard to change our. Also, we can actually give input. All right, if we change. Right, then what we get is 1, 2, 2, 3, 3. What we want is 1, 2, 2, right? And the left node to be null. If we remove if cur, I think I figured it out. We basically want if cur, right, and cur.right, right, does not equal null. Right, then we'll push on cur.left, right, and then to run this, we'll say if cur does not equal undefined, right, then we'll push on the array cur.val. So I think we should actually get what we're looking for. Or maybe not. All right, so we push on, right? And then we get to 2, right? We're gonna say, okay, 2 does not equal undefined, so we're in business. We'll push 2 onto the array. Right, but now we're gonna say, okay, does 2 exist? It does. Okay, does cur error, does the dollars quote, if we do safe navigation to left, right, if it does not equal null, right, then we want to push cur.left. Then we want to push cur.left. I think what I'm looking for is actually, it doesn't equal null. I'm going to print r.x, and I should get undefined, but maybe r.x, property x does not exist on type any. All right, so you do get undefined. So that's what we're expecting with safe navigation, right? Cur does not equal null. Push its value on, array. Say, okay, does the parent value exist? The parent value does exist, right? And cur.left does not equal null. It shouldn't, right? Because cur.left should be equal to undefined. Okay, so it looks like this is, okay. If left is equal to undefined, okay, then it gets set to null. So I think we just had it confused, right? We want to change, okay, now we get it. We want to change this to undefined. I should have took a closer look. This should give us exactly what we're looking for. So 2 would exist, right? And its left would not equal undefined because it would equal null. Right, or we'd push with cur.left is right, we'd push would be cur.left, right? And if it doesn't exist, we'll just push null on, right? Which means we don't want to visit it. I think I see what's happening equals null. So what we want to push on actually is or undefined. I think this is what we want to do. We'll push the value onto the array anyway, right? And if cur doesn't exist, right, what we're going to do is do r.push cur, right, and then continue with the next iteration. That way, everything stays as it was. And you can actually just push the next node onto the queue. And if it doesn't exist, we'll push the null value once to acknowledge it. I don't understand why we're getting so many nulls. It's like a crazy amount of nulls. if we say if cur equals undefined, then we'll just push on a null value. That way, right, whenever it doesn't exist, right, we'll push on undefined. Yeah, I don't understand. We have 2, right? 2 does not equal undefined, right? So we go to the else case on line 27, we push 2 on, then we push on 2's left child, right, which doesn't exist, so we end up pushing on undefined. Then we'll push on null and continue, but we already took it off the queue. One, two, two, null, 3, null, 3. Oh, right. And if it's else, and also safe navigating to undefined is the same thing. Or maybe not when it doesn't. I think I figured out the problem. If you do cur.left safe navigation, it does exist, right? It's not that it's undefined, it is defined. Something's happening here. We're pushing. If it equals no, then we push undefined. When it equals undefined, we push null. Ending with many, many undefines. Even after this undefined, we end up with one more undefined. So how is that possible? I just don't understand. Yeah, I think we ran out of brain juice. I'm sure tomorrow this will be, we'll be able to figure this one out, but I already know we already solved it once, we just wanted this. We know another iterative solution, just wanted a different one, so.